This video is going to be a review of basic ideas from class. Might be, nice just to double check yourself. So I asked you what was the difference between this vector and this vector other than the name. And everybody said this vector is a fixed vector. It refers to the displacement of moving over 2 and up 3 rather. This vector is being scaled with time, which means that we don't actually know how long this vector is unless we give a value to the t parameter. So when t equals 0, for example, this vector is equal to 0, 0, which is just a point. If t equals 1, it's equal to the vector 2, 3. If t equals 2, it's equal to the vector 4, 6, because we've taken this vector and stretched it to be twice as long. This is the way that you denote magnitude of a vector, which is the same thing as the length of the vector. So if I want to know what's the magnitude of the a vector, that's just the Pythagorean theorem because these are the two legs of a right triangle. So over 2, up 3, if I want to know what's the total distance traveled here, or like what's the total displacement described by the vector, it's going to be, let's see, 9 plus 4 is the square root of 13. For this vector, if I wanted to know what's the magnitude of b, the answer is it depends on what the time is. Because remember, for different values of t, this vector is stretched to be different lengths. So if this is describing the length, you shouldn't expect to be able to write a number here until we know what t is. So put differently, the length of the vector is a function of time. If we wanted to calculate what that function was, you can still use the Pythagorean theorem. So remember that if you scale a vector, it scales all the parts uniformly. So that means that we're scaling both the x part and the y part. So you can rewrite this as 2t, 3t. And then if I apply the Pythagorean theorem here, I'll get 4t squared plus 9t squared, which is the same thing as root 13t squared. But of course you can take anything squared out of the square root, so that would be t times root 13, which is just another way of saying that at time t, we're scaling the length of the original vector, which is root 13. We're scaling that length by time. So when I said that time is scaling the vector, it's not just scaling the x and the y, it also scales the length of the hypotenuse, the length of the vector itself. So what does this have to do with speed? Let's pretend I have this vector equation where first I follow the position vector -1, 1, -3, and then I have this vector scaling with time. This describes the motion of an object, and the object is starting at -101, -3, so it's starting way, way, way over here somewhere. And then from that location, it's following this vector that goes over 2 and up 3. And these pictures, of course, are not to scale at all. I'm just giving you a general impression of the locations and directions. So this is the position vector, which is where we start, and then this is scaling. So if time is positive, we are stretching this vector more and more in this direction, which would create the line going that way. If time was negative, we are stretching the vector in the opposite direction, like that. So speed, whenever I ask you about speed, I'm not asking you to recall some procedure that I've shown you. Just think about what speed means. Speed is literally change in distance over change in time. And that makes sense for units too, right? Like change in distance might be a certain number of meters. Change in time might be a certain number of seconds. And speed can be measured in meters per second or miles per hour or any other unit of distance and time. So you can always ask, where am I at time 0 and where am I at time 1? That's going to give you 2 points, and you can find out what is the distance between those 2 points using the Pythagorean theorem. And then you can ask, what was the difference in time? And the answer here is 1, because you set it up that way. So all you need to do is divide the change in distance by the change in time, and you've got speed in meters per second. Or at least you have the average speed between time 0 and time 1. If your object is moving at a constant speed, then that means the speed between time 0 and time 1 is going to be the same as the speed between time 1 and time 2 or any other times. And here we have something moving at a constant speed. This will not be true in general. Like it's very easy to write a vector where it's changing speeds. And in that case, you could still calculate the speed from time 0 to time 1, but that would be different than if you chose two different times to calculate the speed for. So what about this vector equation? Here we have a vector equation where you've got a position vector pointing to 5, 5. And then after that, we've got this vector, which you recognize as a length 1 vector that's rotating around a circle. Except here we've scaled it to be 3 times as long. So really, it's a length 3 vector that's rotating in a circle. So again, my sketches are fairly approximate here. But we're going to get a circle whose radius is 3, centered at 5, 5. Okay, so what if I asked you, what is the speed of the object whose motion is described by that equation? Same thing, speed is change in distance over change in time. So let's choose 2 times. Time equals 0, and I don't want to choose time equals 1 because I don't know what the cosine of 1 is. I would have to use the calculator, and I hate to use the calculator. So let's choose a time that we know about. Let's choose time like, I don't know, let's consider like the first quarter turn here. So that would be pi over 2 is that angle. So that would be a change in time of pi over 2 seconds. What about positions? So where are we at time 0 here? At time 0, we start off at 5, 5 plus 3 times the vector. Okay, so cosine of 0 is 1. Sine of 0 is 0. So if I add these two vectors together, I've got 5 plus 3 is 8. And I've got 5 plus 0 is 5. So 8, 5, which is this point right here. So you can, excuse me, mark this as time 0. Pi over 2 seconds later, I mean, you and I, like, hopefully you can visualize this without plugging in numbers. But we know at pi over 2 seconds, cosine of pi over 2 and sine of pi over 2 are describing the top of the unit circle. So this is where we'd be at time equals pi over 2. So how far did we go? We went around like this part of the circle. So how can I figure out how long that is? I know the whole circumference of the circle is 2 pi r. I know my radius here is 3. So that means the whole circumference is 6 pi. But I'm only doing a quarter, or I'm only traveling along the quarter of the full circumference. So the total distance I'm going to travel here is 6 pi over 4, which is the same thing as 3 pi over 2. So what's my speed? It's change in distance over change in time. So it's 3 pi over 2. That's the change in distance. Change in time is pi over 2. So when I multiply these, the pi's cancel. Well, let's do it this way. We'll do 3 pi over 2 times 2 over pi. So now the pi's divide each other to be 1. The 2's divide each other to be 1. So my speed is 3 meters per second. You may notice that that 3 is suspiciously similar to this 3 up here. And so you might form a conjecture. Maybe the speed is always the same as the length of the vector here. And maybe that's true and maybe it's not true. I think that's going to be a topic that I'm going to assign as a problem-solving exploration, probably between Monday and Thursday for you to think about. Okay, what if I'm writing a vector equation for the motion of a person who starts at 120 and is traveling at 2 meters per second in a particular direction? So let's pretend that you forgot entirely what polar equation or what a polar form of the angle was. How could you approach this? Well, so you know that, let's write it this way. So my position is going to be a function of time. You know it's going to have this form. It's got like a starting location of 120. That's the starting vector. And then I'm going to have something scaling with time that's some vector that's pointing in this direction. And the length of the vector should be length of 2, so that I'm traveling a length of 2 every single second, because I'm scaling with time. And again, like the ratio of the change in x and the change in y should be in a way that I'm sure that I'm headed in this direction. So how can we kind of fill in those missing bits? If we imagine this as a triangle, I want to know what's this distance and what's that distance. So let's write the triangle in this way so that it's kind of easier to look at. So I've got an angle of 30 degrees, and I know that the hypotenuse is length 2. So you can just use SOHCAHTOA. I know that the cosine of 30 degrees is going to be, let's call this delta x, so delta x divided by 2. So what that means is delta x must be 2 times cosine 30. And hopefully this is a familiar pattern to you by now. Delta y equals 2 times sine of 30 for the same reasons. And don't jump to your calculators. You should have memorized what is the cosine of 30 degrees and what is the sine of 30 degrees. So cosine 30 degrees is root 3 over 2. And we're multiplying that by 2. So that means delta x is just root 3. Delta y is 1/2 times 2, so that's just 1. So now that I've got my delta x and my delta y, I can make those describe my vector here, but I have to pay attention to what direction I'm going in. So I want to be going left and down, which means that each of those need to be negative. So my real answer here is going to be 120 as my starting, and then negative root 3 and negative 1. So even though I said let's pretend you forgot about the polar form, all we really did in this work here was convert a polar form to a rectangular form. Because the polar form of this vector would be easy enough to write. We'd just say it's a length of 2 at an angle of 30 degrees. And that is how in our class we're writing the polar form. And to convert it, all we did was imagine a triangle and ask what change in x and what change in y describe that same distance at that angle. What if I wanted to change it so that it's moving twice as fast? Well, right now, whatever this length is, the length of this vector, I'm going that far with every single second, because each time I make t larger by 1, it's like I'm adding another one of those vectors onto the end of my path. So we calculated the length of this vector to be a length of 2. So if I wanted to go twice as fast, I need this length to be 4. And you can do that just by scaling the vector to be twice as large. So instead of t times the vector, we'll do t times twice the length of the vector. So I just multiply it by 2. Now the vector is twice as long, and I'm still going that distance with every second. And if you wanted to, of course, you could multiply this in. So this would be the same thing as saying t times negative 2 root 3 and negative 2. Okay, so obviously if you wanted it to go 10 times as fast, you could scale it by 10. If you wanted to go half as fast, you could scale it by 1/2. So that's a great way of taking your current speed and changing it, scaling it. What if I wanted to figure out how do I scale it to be going a specific speed? And I chose a weird number on purpose, or not a weird number, but a number that's not a normal number for describing speed. The way that you want to do it is you're thinking the length of this vector is how fast I'm going. So in the case of the original vector, this one, I was moving at a speed of 2 meters per second. So we want to scale this whole triangle by some multiplier so that the new speed is whatever we want it to be. So 2 times some scaling factor is going to equal pi. So you can just solve for that directly by writing it algebraically. 2 times some scaling factor, which I'll call triangle. So 2 times triangle equals pi, therefore triangle must be pi over 2. And so that's the number you multiply your entire vector by so that it's the right length. So that's the new length you're moving every second, which is going to give you your speed. So I'm going to take my original vector up here and I'm going to rewrite it. So I'm starting from the same location, 120, except now I'm going to scale it by pi over 2. So we've got t times pi over 2, and then negative root 3 and negative 1. And just like before, you could choose to multiply this in if that feels nicer to you. One of the things that we emphasized was that there are lots of different vector equations that can describe a linear path like this. So if we've got the line y equals 1/7 x minus 2, you know that the y-intercept is at 0, -2. The 1/7 is the slope, so it means that starting from anywhere on this line, if you go right by 7, you will go up by 1. And that's because that's describing the direction that we're traveling, like that's true no matter kind of where you start. So what could we do to describe it as a vector? In general, we could describe this with a vector by first starting with a position vector that leads us to some point that's on the line. And then, added on to that, we'll have a vector that's scaling with time that points along the line itself, like in the direction of the line. And it could be in this direction, or it could be in that direction. So let's just do like a whole bunch of examples. We could do a vector that points straight down to take us to this point, and then a vector that points 7 this way and 1 that way. So 7 in that direction, 1 in that direction. And if you imagine this vector getting longer and shorter, we're pointing to all the different places on this line. So what would that look like? We've got this vector that's going straight down, so that's changing 0 in the horizontal direction, but it's changing by -2 in the vertical direction. And then we'll add a time-scaled vector that is 7 over and 1 up. So that would be a perfectly adequate description. We could also do this. We could do a vector that points down to 0, 2, but then instead of going over 7 and up 1, we could go left by 14 and down by 2. Because that's going to be pointed in the same direction, but it's going to be kind of twice as long in this opposite direction. So an equivalent vector here would be 0, -2 is my starting place, and then time times -14, -2. And the reason they're equivalent is because depending on what t is, it's still possible to have this vector sum points to every single place on the line. Let's do another one. Let's find just a totally different point on the line. So this is 21, 1. Wait, does that make sense? Hold on. Yeah, okay, that makes sense. So 21, 1 is also a point on the line. So let's write a vector that starts at that location and then moves left along the vector. So I could have a starting point of 21, 1, and then let's scale it with time. And this time, let's move left by 7/3, and let's move down by 1/3. So what that means is I'm starting here, and then I'm moving left by 7/3 and down by 1/3. But the slope is still the same there. So I know I'm still moving in the direction of the line. And now again, depending on what the t variable is, as t changes, this arrow is stretching to be different lengths, and I know I can stretch it to be any length I want, which is why I know that whole equation ends up pointing at every single position along the line. So I guess the point is, you can do it in lots and lots of different ways, and the reason why you want to do that is just for convenience. Like, maybe you're trying to describe the motion of something, but you want the person's motion to start here at time 0 and go left. Or maybe you want the person's motion to start here at time 0 and go right. So this gives you the freedom of describing whatever starting position and whatever speed and direction you want. Okay, let's do one last problem. What if I've got a fixed vector, it's not moving with time, but I just want to rotate that vector by some angle? So I think it's always helpful to visualize what's happening. So vector p describes a displacement that goes over 8 and up 1. So it's going to be, approximately like this. If I want to rotate through an angle of 120 degrees, so it's helpful to kind of visualize what this looks like. So if I'm rotating this 120 degrees, I'm imagining first, let's rotate it by 90 degrees, and that's what this dotted line is. And then let's rotate it by another 30 degrees, because that would be 120. So these two vectors are supposed to be the same length, but they're pointed in different directions. And we don't know what angle theta is, because it's whatever the arctangent of 1/8 is. But I do know that that same theta is kind of over here. Okay, so what are we going to do? So you could use two approaches, and really they're probably going to end up being equivalent in the end. If you have a nice diagram like this, think clearly about what do you want to find. If I'm going to write the rotated vector in rectangular form, I want to know what is this delta x and what is this delta y. So you could ask yourself, what do I need to know in this picture to figure that out? So if you could figure out what the length of this hypotenuse was, if you could figure out what this angle was, you could probably solve for delta x and delta y. An alternative would be rewrite your original vector in polar form, because polar form is a distance at an angle. And then it's easy to rotate things in polar form because you just add to the angle. And then once it's in polar form, convert it back to rectangular form to figure out what the new delta x and delta y are. So I'm going to kind of show you this approach just because I feel like it takes less wherewithal than like drawing your diagram correctly. So in polar form, the distance is just Pythagorean Theorem. It's the magnitude of your vector. So in our case, 8 squared is 64 plus 1, so that's root 65 for the distance. Theta is just the inverse tangent, or the arctangent of 1/8. And that's something that you could use your calculator for. Or if you don't want to bother with the calculator, you could just label it with a letter. Let's call k whatever number this is. And so instead of writing a number here, you could just remember this letter k represents whatever that number would be if you plugged it into the calculator. Okay, so in polar form now, we've got that it is some number k. Oops, no, that's the angle, sorry. We've got that it's a distance of 65 and an angle of k. All right, so what happens when we rotate it? If we're going to rotate it by 120 degrees, let's make sure k is in degrees, and then we'll add 120 to that. Great. So now how do you take that and convert it back into polar? Well, convert back into rectangular. So what you do is you've got some angle, k plus 120. So where is that? 120 is about there. So k plus 120 would be who knows where, somewhere over here. And you know that this length is root 65. So the delta x, this is just like we did earlier, right? Delta x is going to be this length, which is root 65, times the cosine of whatever that angle is. And delta y is root 65 times the sine of whatever that angle is. Okay, so I guess let's do all the calculations. Later in the year, you'll actually learn a more precise way of calculating this than the calculator. But for the moment, my calculator is telling me that arctan of 1/8 is approximately 7.13 degrees. So let's add 120 to that. So that means that, so k was 7.13, so that means that my new rotated angle, which I'm going to call A, is 127.13. Cool, so 127.13 isn't clearly larger than 180, it's more like up here somewhere. So let's draw a new picture maybe. So it's going to be like here-ish. So what? Oh yeah, right. So now this is length 65. So now root 65 times the cosine of 127.13 degrees. And remember, if you're working in degrees, that's not the natural way that cosine and sine are defined. So you have to make sure your calculator is in degree mode. But you can calculate what those are, and they end up being negative 4.866, etc. And this is actually, there's a more exact form for this, but that's not the focus right now. And 6.427. So you can rewrite your rotated vector as those displacements. Negative 4.866. And this is again approximate. and 6.427. Okay, I hope that was all a helpful review for you. I'll see you on Monday.